Hello there, my name's Gary Sims and this is Gary Explains. Now I hope you've had a chance to look at some of my videos about the power and the performance of different microcontroller boards. So that's like the Raspberry Pi Pico, Arduino boards, Cortex M3, Cortex M4 boards, Blue Pill, Black Pill and so on. I've got a couple of videos about that, including the latest ESP32-S3 board, which has a RISC-V processor. Now the next step in that series is to measure the power and the performance of microcontrollers that have two cores, dual core. And that includes the RP2040, which is in the Raspberry Pi Pico, the ESP32 and the ESP32-S3. So in this video I want to look at how you can program those three different microcontrollers from within Arduino and use both cores. So if you want to find out more, please let me explain. Okay, so in a moment we'll be jumping over to the Arduino IDE. We're doing some coding to look at how you use both of these cores. At the surface, the way you do it on the Raspberry Pi Pico is different to how you do it on the ESP32. So I'm going to show you both of them, and then in the end we're going to come up with a unified sketch that actually works on both systems. So you can use that as a template. It will be available on my GitHub repository, and you can take that and start using it yourself, knowing it will work on whatever microcontroller board you pick from ESP32 or from all the Raspberry Pi Pico or one of the compatible boards, for example. And I'm also going to be taking a quick look at mutexes so you can see how data can be passed from one core to the other. Okay, let's get cracking. Okay, so let's start with an example of how you do dual core programming using a Raspberry Pi Pico, or more specifically the Raspberry Pi 2040 microcontroller, because in fact in this case I'm using the Seed RP2040 board, very tiny little board, very nice, and I'm going to use that, completely compatible of course in terms of software with the Raspberry Pi Pico. Now normally in an Arduino sketch you would have setup and then you would have loop, and that's pretty simple. So setup gets run once at the very beginning, and then loop gets run round and round and round and round again forever and ever as the microcontroller is running. Now when you want to have dual core setup, what you actually have is you have a setup and then you have a setup 1. So this is for core 0 and this is for core 1. In fact, it says here Arduino code will automatically normally execute on core 0 and the second core sitting idle and in a low power state. When you have setup 1, that gets run on core 1. So what we've got here, well, what we normally do is we just set up the serial. That's easy enough. And I've got two variables, count 0 and count 1. One is going to go from 0 upwards, the other is going from 1,000 downwards, and we're just going to print them both out using each core to do that. Very simple work, of course, for the Raspberry Pi Pico to do, but just gives us an example. So here is our normal loop thing, and all we do is we just say, well, print out on the serial loop and then count 0. So that's all we're going to do, and then we're going to add 1 to count 0. If it gets to 1,000, put it back to 0 again. So we're going to keep going 0 all up to 1,000, 0 up to 1,000, just keep going round and round and round. And we're just going to delay for 1 second before we do it again, so we don't just get loads and loads of fast scrolling stuff. But here's the thing, now if we add loop 1, then this automatically gets run on the second core. It's literally that simple. You just need to run this second function automatically on the second core. And what we're going to do in this is we're going to print out loop 1 and we're printing out count 1, a different variable, and we're doing minus here. And we're going to delay for a different amount of time, so you can see they're both running kind of not synchronized. They're running out of sync with each other, one every 2.5 seconds, one every second, and they just get run. So really simple, look at that, not much code. We've just got setup 1, loop, and loop 1, and that's it. That's all you need, and you're actually up and running doing dual core programming on a Raspberry Pi Pico. Okay, let's run that and see it in action. Okay, so here we can see it running, and basically we can see that loop, which if you remember back to our code is just this one here, that's what's running inside normal loop, prints out 2, 3 numbers at a time, and then you get another one from loop 1, a bigger number, 995, 994, because it's going backwards. So that's here, loop 1 is being printed out, and of course it's pausing every 2.5 seconds, it's running every second, so they're going to be interleaved 2 or 3 numbers. There's 2, here's 3, here's 2 again, and that's happening. So that's now happening, 1 on each core. The bigger numbers are on one core, the smaller numbers are on the other core, and that's it. You didn't have to do anything. You just literally created a second loop, and it actually worked out of the box. Okay, so how do we do the same thing on an ESP32 board or an ESP ESP32-S3 board, both of which are dual core boards from Expressive systems. So we have to do some things slightly different. Expressive systems, in fact, are all built on top of FreeRTOS, and then they've kind of taken that and added in this kind of Arduino compatibility, but underneath there's some FreeRTOS stuff going on. But of course, let's just start with the easy stuff. There is, of course, a normal setup function, and we have a normal loop function, very, very similar to what we had with the Raspberry Pi Pico. One thing to note here that's different is that I'm using this new function called export get core ID, and this is a function that the ESP32 framework provides to Arduino from FreeRTOS. It's not a standard FreeRTOS core, but you get it here on this side. It just tells you which core are you running on. So here we're just saying print with the loop, and then we're going to print out the core number, so we know which one this core this is running on. And that's exactly the same here. We're just sleeping for 1000 while we're doing all the counting there. And look here, we've also got a loop 1, exactly the same. And again, we're going to print out to find out which loop it's on by getting the number, and it's doing from 1000 bound to 0 with a delay of 2 seconds. So this part of the code is very, very similar to what we had on the Raspberry Pi Pico, except we've added in this thing to get the core ID. Now, I've also, if you look at it, we've actually got this setup 1 as well, which sets count 1 to 1000. But to do this, I've actually had to put in an extra bit of plumbing, and that plumbing we find here at the top. And what's that here? Well, first of all, we need to define a task handle. This is something that comes from FreeRTOS for loop number 1, for that second core. And then I've created a special function here called ESP loop 1 that does what? It calls setup 1, and then in an infinite loop it calls loop 1. So I've kind of provided the plumbing here for the ability to run a function over and over and over again inside of loop 1 and call setup 1 just once, and we've called that loop ESP loop 1. And then there's a bit more here. You add in this function call here, which is basically, again, a call to something similar to what you get in FreeRTOS. It's a function they've brought over for the Arduino, for the ESP32, but basically create a task. What task? Well, ESP loop 1, that's what we've just defined up here. Okay, and it's going to have this handler, the variable to know about it is task loop 1, which I defined up here. And here's the important thing: I want you to run it on whatever the Arduino code is not running on. This is a macro that's defined that tells you whether Arduino code is running on core 0 or on core 1, and whatever core it's running on the opposite one. In fact, look, pin to task to core. Pin task to core, I just put that there because that was a bit of a typo, that shouldn't say that. So it runs it on the opposite one to whatever it's running on. So if you include this call to create pinned task, and you include this little bit of plumbing here, then down here you can automatically use setup 1 and loop 1, and it runs exactly the same. So there's a bit of code that you can actually take a Pico kind of stuff and you can get it running on your ESP32 board. In fact, in a minute we're going to look at how you combine all this together so you get template code that runs on both systems without any problem. Okay, so let's run that. What we're going to see loop 0 and loop 1, one of them going from 0 upwards, one of them going from 1000 downwards, just as we saw with the Pico. So let's run that and see what happens. Okay, so here it is running, and we can see exactly the same thing. We've got the higher numbers going down, running on loop 0, and we've got the other code starting from running on loop 1. Now, that's interesting because actually it was the other way around when we did it on the Pico, and the reason for that is you've got this setting up here, tools, Arduino runs on, and actually it runs on core 1 by default. Now, you can switch this to core 0, and because we're using that clever thing here, I just say whatever the Arduino is running on, put this other function on the other core. You can have it either way around, it automatically copes with it. So if you use that little trick, it will cope whether the Arduino loop is running on core 1 or on core 0. Your other loop will run on the other core automatically. So that's just a great way of getting that just working without having to worry about which core things are running on. Okay, so what I've got here now is a unified template code that you can use. All this, of course, will be in my GitHub repository that will allow you to run both RP2040 and ESP32 and ESP32-S3 on all the same code on dual core without having to worry about which platform you're on, because I've built all that in here. So first of all, what's this first bit here? So what we're saying to the compiler is if it's ESP32 platform or it's the RP24, and there are two ways of recognizing that, then it's fine. If not, print out a message at compile time saying this is an unsupported platforms. If you try to compile this for, let's say, the blue pill or the black pill, you're going to get that message come out so that you know that you're doing things wrong. You can't do it like that. And then what we do here is we intermingle the code with some definition. So for example, if we know we're running on the ESP platform, then we put in this plumbing that I put in earlier, the ESP loop 1 and the task handle and calling loop 1 forever, but it only includes that code if we're using the ESP32 or the ESP32-S3. And then likewise, if we are actually using the Raspberry Pi Pico or one of its compatibles, then we need to include the free RTOS header, because that's also supported. And one other clever thing, I use this export get core ID, which is only available on the ESP32 platforms, but on the Raspberry Pi you actually use get core num. So I've actually made these two synonymous. When you call this on the Raspberry Pi, I'll actually call this, and then we get both functions. And again, we don't need to start worrying about, oh, which platform am I on, which call do I make. We'll just start writing the same code. And then again, back in here in the setup, similar thing. We only call the X task create pinned to core if we're running on an ESP32. If we're not running on ESP32, then loop 1 is automatically called by the Arduino implementation. And then down here, as you can see, everything is the same, even the call to export get core ID, because on the Raspberry Pi Pico it will call the get core num, and it will just work. So here we are, exactly the same code, and now this will compile and run on either platform. Okay, let me give you two demos just to show you that. So now we're currently on ESP32, so let's just compile and run that. So here we can see running on an ESP32 board, that generic code just compiles out the box, and as you can see, we've got the numbers going up and some going down depending on which core it's running. Okay, run the same program on the Pico, won't be any different, it'll look exactly the same, and that's of course the whole point, it will look exactly the same. Okay, let's put a Pico in there and try this. So here we can see the same code running now on the Raspberry Pi Pico. Loop 0, loop 1, one's going from 1000 downwards, one's going upwards, exactly the same. So now you've got some template code that you can just use for all your projects that you want to do dual core stuff on. And it doesn't matter whether you've gone with the ESP, the ESP32, the ESP32-S3, or the Raspberry Pi Pico. You can get it to work just by using this setup 1, loop and loop 1, and the code just works as long as you use this extra plumbing up here that I've put in. Okay, now the one thing that remains is how can you get the two cores to maybe, you know, get some data sharing between them. Let's have a look at that, and again a unified model that works on both platforms. Okay, so here is our unified dual core example with locking. Now what's locking mean? Well, basically if you've got two cores running independently and they want to share data, you've got to make sure they don't bump into each other. They make sure they don't, you know, try to do the same thing at the same time. It's called race conditions. It's called the read-writer problem. In fact, I've got a video here on this channel about the dining philosophers problem. Very similar problem. Two things independently are trying to grab hold of the same information. Now, if you do want a video on semaphores, mutexes, and critical sections and general synchronization between two threads, whether that's on Windows, Linux, or on you know, on Arduino, do let me know and I'll do a video just about that. But what have we got in here? All the same stuff here, everything's the same. One difference is here is that I've had to include this header file semaphore, semaphore.h here. For the Arduino. For the ESP32, it's automatically included. And now here we've got a new number which is called rnum. It's going to be a random number, and basically one thread's going to set it and the other thread's going to read it. And so now you can kind of see that we're passing information between the threads. One will actually read it and the other will write to it. So to do that, I've basically got a quick dirty hack of a function here that actually does random numbers. Interestingly enough, this used to be the random function number function that was in VAX VMS for many, many years. It produces reasonable random numbers, not what you'd want to use for encryption, but good enough for just about anything else. So that's just a nice little function there that does that. And so if I call simple random long, I'll get a random long number. Now here's where the interesting part starts. We've got some locking code here, and I end it down here to show the end of the locking code so you can see what the code is. Now we've got a few things going on in here. First of all, we have to create this semaphore In fact, it's going to be a mutex, but in FreeRTOS, it still calls it a semaphore because they're based one on the other. And I'm calling it big lock. Okay, so I've got some lock helper functions here that allow us to kind of lock and unlock this mutex based on a semaphore. Now, of course, I could do this in C++ with a class and member functions. Absolutely, that would work as well. I'm just sticking here with some very simple C functions. So basically, we've got big lock, and it goes into this while loop. It says if the lock has been created, of course, that's the first thing. We want to make sure it's actually active and there. It says if it's been created and you try to take the lock, if it fails, just wait 1 millisecond, go around and try again. Now, most of the time it succeeds straight away because we're dealing with milliseconds here and both processes are kind of just, you know, they're not exactly thrashing it out here, but this is the whole point. You need to make sure you protect the resources. So it just goes around here and tries to get the lock. And once it won't leave here until it has a lock. So that's really important. Once you call big lock, it goes into that function. It doesn't return until it has the lock. And that means only one of the two cores can have the lock at one time. They both can't own it at the same time. So you lock it. You say, I'm having that. And then we've got the inverse function here, unlock, and that calls this FreeRTOS function give semaphore give, which releases the lock. So it's a give it back. Okay, so here you take it, and here you give it. Now, of course, you don't have to wait for the give because once you've given it, that's it. You just give it and you carry on your way. So there's no loop here. So these are two ways of locking and unlocking. Now, we've got some functions here. Set rnum. Remember, rnum is this number that we've got up here, and we're going to use a random number to set it. So set rnum, what does it do? It calls the lock. If it can't get the lock straight away, it'll wait a millisecond, keep going round until it can get the lock. Okay, and then it says, okay, set the rnum to whatever number we passed in here, which we'll see in a minute, which is going to be a random number. And once you've managed to do that, unlock it again. So basically you say, hold on, lock it, set the number, unlock it. And while it's got the lock, the other thread can't be doing anything with it. And we've got the same for the get the R number. So we lock it, okay, then we say, find out what it is. Once you've got it, you can unlock it and then return and say, here's the number that I got. Now, two things to note here. Often you don't need this for read. Okay, this is what's called the reader's writer's problem. If you don't have it for read, the worst thing that can happen is that it's been updated and you get the old value because it was in the middle of reading it when it got changed. Now, read is generally atomic, but it won't get, so you won't get a corrupt number, but it could be one sequence behind. Now, if you want to make sure it's not like that, you need to lock it. The other thing to notice is make sure that you assign this to a variable, local variable, and then return it after you've unlocked. If in here you just did return rnum, then it would never unlock and your program would lock up freeze because it wouldn't be able to go any further because the lock would be permanently held and no other function would be able to go any further. And that's the end of the locking code. So what do we do? Well, we have our normal boilerplate code here for setup number 1, and all we're doing is extra in here is I'm saying set the R number to simple random long, that's our little random number function, set the rnum, which means it would get the lock, set the rnum to that number, unlock it. Okay, and in the other loop, we're actually, I changed the printf here to actually print out the result of get rnum in brackets there. So it's going round and it says, I want to read the number, take the lock, read it, unlock it, and go on. And if they ever both come at the same time to try to change it and read it, one of them will have to wait while the other one completes. And that way you make sure that nothing actually untoward or any corruption happens in your code. Okay, let's run the code and just see it running. Okay, so here we can see it running, and basically loop 0, which is counting upwards, that sets rnum, and loop 1 reads it. And remember, I've got that printf statement here that prints out get rnum. So we know it's changing every time. And how is it changing? Well, because loop 0 is changing it and loop 1 is reading it. So there you go, a synchronization using the same bit of memory, and what's happening is that one thread is changing it and the other thread is reading it, and they're locked to make sure that there's no collision going on between them. Okay, that's it. My name's Gary Sims and this is Gary Explains. I really hope you enjoyed this video. If you did, please do give it a thumbs up. If you like these kind of videos, why not stick around by subscribing to the channel. Also, if you've got any ideas about what else I'd like to see in this series of videos, please let me know in the comments below. Don't forget you can follow me on Twitter at Gary Explains, and I also have a monthly newsletter. Go over to garyexplains.com, type in your email address, no spam, but you will get the newsletter. Okay, that's it. I'll see you in the next one.